This will be about the least favorite thing in this chapter, balancing redox reactions, and I'm really, really sorry. So balancing redox reactions, definitely more difficult than balancing regular reactions, right? Because you got to keep track of the electrons. And the key is that redox reactions are electron transfer reactions. The electrons that are lost by the species that gets oxidized have to be the same number of electrons that are gained by the reducing species, because that's where they come from. So in this case, again, the species that's oxidized, transferring electrons to the species that's getting reduced. So if we look at some examples here, H2O2 plus PBS there's a couple of different ways you'll often learn to balance redox reactions. So I'm going to only teach one. It's usually the one you guys will see presented, the half reaction method. And it's usually just the little bit easier and less likely to make mistake method, if you will. So hence we're going to go there. If you look here, so in a reaction like this, you can probably pick out who's getting oxidized and reduced. And what you'll find is that here oxygen is -1, like we assigned earlier, whereas here oxygen is -2 on the other side. So, and the other place you'll look is you'll find out, if you assign all of them, is that here sulfur is -2, whereas here sulfur is +6. Those are the species that are changing. And what you want to do is set up half reactions. So one is the oxidation half and one is the reduction half. Now let's look at this for a minute. Which element specifically looks like he's gaining electrons? Oh, it's tricky here. Notice if I gain money, what happens to the value of my bank account? It goes up. But when you gain electrons which are negatively charged, your oxidation state doesn't go up, it goes down. That's why they call it reduced, because the oxidation state goes down. And so in this case, oxygen's going from -1 to -2, that's reduction. Oxidation then is the opposite. When you go from -2 to +6, that's going up. It's going up not because it gained, because it lost. It seems so backwards because we're dealing with negative charges. That's kind of the way things are defined here. And so in this case, we'll set up two half reactions. So, and we'll use the element that's getting oxidized in, or sorry, reduced in one, and the element's getting oxidized in the other. Cool. So the element that is getting reduced is the one gaining. It seems backwards because when you gain, you usually think when you gain something, you go up. But when it's electrons that are negative, when you gain, you go down in oxidation state. And that's why they call it reduced. So if that ever seemed just a little bit backwards to you, now you know why. Okay, so we set up our two half reactions. So this one's going to be our reduction half reaction, -1 to -2. This one's going to be our oxidation half reaction. So, and you balance all of the elements, and you save oxygen and hydrogen as the last two elements to be balanced. So in the first one here, all I have is oxygen and hydrogen. In this one, the elements I have besides oxygen and hydrogen are lead and sulfur, and there's one of each. Those are already balanced. The last two elements, you always do oxygen second to last, and hydrogen is always last. So to balance oxygens, redox reactions are always aqueous, and when you're balancing oxygens, you always add water molecules to balance those out. So in this case, are the oxygens balanced in the first half reaction? No. Which side needs more oxygens? Right side. So I'll add water. In this case, we already had water, so I'll put a coefficient there in this case. Cool. And now we got to balance, because we've added waters, we've adjusted the number of hydrogens, which is why you save hydrogen for the very last. Which side needs hydrogens? Left side. And so in this case, when you balance out hydrogens, you always add H+ to balance that out. Essentially acid, if you will. How many H+ did I need to add? Needed 2 of them to make this balanced. Cool. For the second one, I got to balance the oxygens. So what do I do to balance the O's? Yeah, I need waters to balance those out. So which side needs the waters? This side. How many? Good. 4 oxygens, I need 4 water molecules. And so now how do I balance the hydrogens? Yeah, I need 8 hydrogens on the other side. And what do I add for hydrogen again? H plus, and I need 8 of them. So that's the special rule here. Anytime you're balancing oxygens out, add H2O. Anytime you're balancing out hydrogens, add H plus. Okay, these still aren't balanced. Once you're done with all the elements, the last part in a half reaction is the electrons. So, and there's a couple of different ways for looking at the electrons. Now, one, you could look at oxygens -1 right there, and it's -2 right there. To go from -1 to -2, are you losing or gaining? Gaining. And how many? 1 electron. But there's 2 oxygens that are doing it for a total of 2 electrons. Now, that's not my favorite way to look at it, because there's a much easier way without ever even, technically, you wouldn't even necessarily have to get the oxidation states to do it this way. You just balance out the charge. In a properly balanced half reaction, the charges should all be balanced. What's the total charge of everything right here? Well, this molecule doesn't have a charge, and this ion has a +1 charge, and there's 2 of them. And so the total charge is +2. What's the total charge on this side? 0. And I add electrons to whichever side is more positive till both sides have the same charge. So which side needs electrons in this case? This side, and how many? It needs 2. And now both sides would have a 0 charge. And again, my goal is not necessarily to get to 0. My goal is just to get both sides the same. And so again, I always, last step, add electrons to the more positive side till both sides have the same charge. Okay, so in the second one here, what is the total charge on the reactant side? Yeah, water 0, it doesn't matter that I have 4 then. PBS is 0, so overall it's just 0. And what's the total charge here? +8. Which side needs the electrons? Right side, how many? I need 8 electrons till they're both the same charge. So these just happen to balance out to 0, but again, my goal is not to get to 0, it's just to get to the same charge on both sides. So here's the deal. When electrons are a reactant, those are being gained. When electrons are a product, those are being lost. This is the reduction half reaction. The second one here is the oxidation half reaction. So when electrons are on the reactant side, they're being gained by the reactants. But when electrons are on the product side, those are electrons that have already been lost. They were the lost reactions. So when electrons are on the reactant side, that's a reduction half reaction. When electrons are on the product side, that's an oxidation half reaction. So in this case, the first half reaction is showing me where electrons are gained. But the second one's showing me where the electrons are lost. But it's the same electrons, because the electrons are just being transferred from the species that are losing the electrons to the species that are gaining them. So those electrons there and those electrons there are the same electrons. And so the last step is when you go back to combine these, you have to balance out the number of electrons. And so in this case, this is a 2-electron process. This is an 8-electron process. What is the least common multiple between 2 and 8? Yeah, what? 8. What number do they both evenly go into? 8. And so in this case, I need to make both these 8-electron processes. So I'm going to leave this one alone. But the top one here, I've got to multiply the whole reaction by 4. The whole thing, every coefficient. And so in this case, this coefficient is going to become an 8. This one becomes an 8. This one becomes a 4. And this one becomes an 8. I told you guys are going to hate this. And now you add them back together, combining all the reactants on one side and all the products on the other. And because now I have 8 electrons on one side of this one and 8 electrons on the other side from this one, they're going to cancel. And in any properly balanced complete reaction, the electrons should not be there anymore. So in this case then, putting it all together, so we're going to have 8 H plus 4 H2O2 plus 4 waters plus PBS forms 8 waters plus PbSO4 plus 8 H plus. because H plus in water is used so often in a lot of half reactions, you're probably going to have a fair chance you'll have some on both sides. You need to cancel out whatever's in common. So what do I need to cancel here? Yeah, 8H pluses cancels out 8H pluses. What else? Yeah, these 4 waters are going to cancel out 4 of the 8. So how many will I have left? 4. Cool. And so now our complete balanced reaction here Cool. There's your complete balanced reaction question.
Sorry, for the peroxide on the top redox, why is it 4 instead of 8?
Well, if you notice here, what was the coefficient before I put the 4 there? There was no coefficient, which means there's a 1, right?
Oh,
and so I multiplied every coefficient by 4 because I quadrupled the reaction. 4 times 2 is 8. 4 times 2 is 8. 4 times 1 is just 4, though. Cool. Here's the deal. There's one last little part to this. You guys are like, oh my gosh, really? Yeah, really, sorry. So redox reactions can be balanced in acid or base. The default method here, because we add H plus by default to balance H's, by default we're always balancing an acid. And so if they want you to balance in base, you have one extra step. Now here's the deal. We lucked out on this one. Could you tell that I balanced this in acid by the time we're done? No, because there's no H plus in this one, whether you balance it in acid or base, that's the answer. There's no difference. But for the next one we do, you'll see a difference. And they could ask you either way. For balancing in base, you have one extra step at the end. Like I said, big pain in the butt for balancing redox.
Now, with this balancing, you don't worry about if it's a liquid or a solid or anything like that?
So as far as the balancing goes, I didn't worry about liquids and solids and phases. I mean, technically we could put it in. And technically, things have to be in the same phase, but you're almost always dealing with just liquids and aqueous, occasional solid or something, but phases aren't so important as far as the balancing goes.
Okay.
Other questions? You guys ready to see one more of these? Question?
What would the question be like, balance this equation?
So the question's not going to be balance this equation because what kind of questions do you guys have on your test? Multiple choice. So you could get the question in one of a few different ways. You could get, which of the following is the properly balanced equation? Okay, great. So, and there's a shortcut here because in any properly balanced equation, the charges should all be balanced. And here, total of 0, total of 0. It may not be 0, but it should be the same on both sides. So that's one cheat. You can at least get rid of some wrong answers maybe there. So, but the other way they ask this, they'll say, what's the coefficient in front of water in the balanced reaction? And it's 4. Or they could say, what is the sum of all the coefficients in the balanced reaction? What is the sum of all the coefficients here? Don't say 8. It's 10. It's 4 plus 1 plus 4 plus 1. So if they ask it that way, don't forget, if there's no coefficient, it really means there's a 1 there. So be careful. No, just what's the sum of the coefficients of all the species in the reactions, usually the way they ask it, if they're going to ask it that way. But again, more commonly though, is they usually just ask what's the coefficient in front of any one of these or something like that. All right, let's do one more of these guys. All right, so if we look at this here, a couple things we can do with this thing. So we can split it into half reactions, get it on our way to balancing. So how would you recognize this is not balanced or anything, but what's the dead giveaway here that this thing is a redox reaction? How, without even assigning charges, oxidation states, would you know that something changed? -1 here going to 0 here, elemental form. So when you see something in its elemental form, if it's in the elemental form on one side, it's almost can't be in the elemental form on this side. There's a couple exceptions, but usually that's the way it works. So here it's 0 and here it's not 0. And so dead giveaway, something changed. Yeah, it's redox. So in this case, it also makes it easy in setting up your half reactions. Pretty much you're going to have I minus going to I2 in one of them, and then MnO4 minus going to Mn2 plus in the other one. Okay. Somebody start me off on the first one. Balance all the elements. What are the last two elements to balance? What are always the last two? Oxygen and then hydrogen. So balance everything else first for me. What do I need to do? I need a big fat 2 there. And technically, you really should balance the elements that's changing first, and it's the iodine that's changing. Okay. So which element in this next one is changing? Who's changing oxidation states? Manganese is changing. It ends up at +2, but what did manganese start out at? +7. Oxygen's -2, and there's 4 of them. To get to a total of -1, manganese had to be +7. So he's gaining 5 electrons. Awesome. So in this case, then, the manganeses are balanced. So in the top one, all the elements are balanced. That's all I had. What do I do next for the lower one? I have to add what? What do you do to balance O's? Not OH. What do you add? You add water. You add water for oxygen. So how many waters do I need over here? 4 waters. Now what do I do? Add H plus, how many? 8. Cool. And now all the elements are balanced in both of these. So the last step is balancing out the charge by adding electrons. So what's the total charge on this side? -2. What's the total charge on this side? 0. Which side needs the electrons? Whichever side is more positive needs the negative electrons. Which side is more positive? Product side is. How many electrons do I need? 2. So again, the goal is not to get to 0. The goal is just to get to where both sides have the same overall charge. Notice this side's now -2, and because we added those, this side is now also -2 total. So the electrons always go on the more positive side. What's the total charge on the reactant side for the second one? It's +7. We have 8 H pluses and 1 MnO4 minus. What's the total charge on the product side? +2. Which side needs the electrons then? Well, this is the more positive side, and how many? 5. And somebody kind of already pointed that out. Notice it's just often easier to get the electrons this way because you never actually have to assign even an oxidation state to get here. You just balance out the charges. Okay, this top one, is that oxidation or reduction? That's oxidation. Electrons are produced. Those are lost electrons. Here, electrons are being gained, so this is reduction. How do I make the electrons balance here? Yeah, I got to multiply this top reaction. Let's do this in another color. Got to multiply the whole reaction by 5, and the bottom one by 2. That way, it's balanced out to being a 10-electron process. Cool. And then we'll put it all together here. So we're going to end up having then 10 I minus plus 16 H plus 2 MnO4 minus going to 5 I2 plus 2 Mn2 plus 8 waters. Is there anything that's going to cancel? Can't reduce it either. Notice there's no common multiple here or anything like that. So all the way across. So in this case, this thing is balanced. And if our question was balance it in an acidic solution, this would be the answer. So, well, again, the question's going to say it. The question says balance this in acid, or the question says balance this reaction in base. So if the question had said in acid, this would be our answer. But if you balance in base, which we're going to do next, you have one extra step you got to do.
But you can't tell that that reaction's acid.
Like if they gave us options and said which one of these are acidic.
They're not going to do it that way. The question is always balance the following in acid or balance the following in base. But notice, you could tell this was acidic because somewhere in my reaction, how do I know there's acid in there? H plus. Guess what needs to happen for me to balance this in base? I got to get rid of the H plus. Well, we don't get rid of it. We neutralize it, as we'll see. Question. Why doesn't the I disappear? What do you mean?
Like, because there's 10 on one side and
Ooh.
10 on the other.
Careful. The elements are always balanced. I have 10 I's and I have 10 I's. I have 2 MNs, 2 MNs. But are these exactly the same compound, form, element, ion? No. That's why they don't cancel. It's only when they're exactly the same in every way that they're going to cancel. So in this case, if you're balancing an acid, we'd be done. But if you're going to balance in base, you got one more step to do. In a highly basic solution, you'd have a lot of hydroxide. And what would the hydroxide love to neutralize? The H pluses. How many hydroxides do I need to add then to neutralize all of those? 16 of them. And when I do that, what is it going to form? Water. How many? 16. I got a problem though. Before I did this reaction was balanced. Is it still going to be balanced? No, which means if I added 16 OHs to this side, I better add 16 OHs to this side. And now it will still be balanced. On this side, the 16 H pluses and the 16 OH minuses combine to form 16 waters. But on this side, the 16 OHs are just going to stay there. And so now let's put it all together. We're going to still have 10 I minuses. We now got 16 waters on this side. 2 MnO4 minuses. 5I2 plus 2 Mn2 plus 8 waters plus 16 OH. And again, because we just formed a bunch of waters, and waters are so common in redox reactions, we might see if we're going to have some waters cancel. Are we going to have some waters cancel? Yeah, where are the waters going to cancel? Yeah, these 8 waters will cancel out 8 of the 16, which means how many have I got left? 8. And now, what remains? That's exactly what I wanted to hear, actually. So she said, this would be so crappy on a test, it would take like 20 minutes. Okay, let's do some shortcutting here, right? So let's look at a couple things. What if the question had said, what is the coefficient in front of MnO4 minus in the balanced reaction? Well, then once I got here, I would have stopped. I'd have been done. Now water, H plus, those things you got to be careful because those come from all over the place and coming from multiples and stuff. But this, it only shows up right there. I doubled this reaction. Its coefficient is going to be a 2. Done. End of story. Don't have to finish it. So if you get an easy question like just what's his coefficient or what's his coefficient or his, that's not a bad question. Now, if it's all about water or H plus or OH minus, then you might have to go all the way. But any of the other species, it's a lot easier. So yes, thank you. This bottom one is balanced. In base. And again, the question itself will tell you how you're supposed to balance it. If it says balance at an acid, we would have stopped way back up here. But if it says balance in base, you got to carry it all the way out down here.
How did your waters cancel? I think I missed.
So I had 8 waters. And so we had 16 over here. 8 of them canceled, so I only had 8 left. But both sides, 8 waters from both sides canceled, yeah. Okay. Yeah, so we lost 8 of the 16 here to have 8 left. And we lost all 8 of them right there on that side.
Oh, I get it. Yeah, I was trying to wonder how to get that tool with that.
Okay. You guys cool with this? What's your question?
So if they say that balance it in base, then you end up with no hydrogens?
Yeah, in a basic solution, if it's balanced, you should have no H pluses anywhere. Just like in an acidic, you should have no OH minuses in the balanced reaction.
You don't have to have hydroxides for it to be base.
Well, here's the deal.
If you have
If it's balanced in acid, you'll probably have H+. If it's balanced in base, you'll probably have OH- in it. Notice the first one we did was an exception. That didn't have H+ or OH- in it, and so whether you balanced it in base or acid, it'd be the same reaction either way, the same answer. But most of the time, this is what H+ is the evidence that you balanced it in acid, and OH- is the evidence that you balanced it in base. Welcome. You guys ready to move on? That definitely takes some practice. So practice a few examples of balancing reactions. Got a couple other things to talk about. So we got to talk about what's called the oxidizing agent and the reducing agent. And this is where things get a little bit annoying. So remind me of your name. Michael, you're kind of in my front row, so it's all worked out good. So one thing you guys need to know about Michael is Michael has $6,000 in his back pocket. So, and if you think you're going to mug him on his way out tonight, I call dibs. I'm going to mug him. So, but I don't want to get implicated in this. So I'm going to hire my wife to do it instead. So she's going to mug him. She's much better at that sort of thing than me as well. I don't want to get my hands dirty, but she'll kick your butt, dude. She's really good with a handgun. But anyway, so she's going to be the agent I hire to take your money. Well, I lied. Michael really doesn't have $6,000 in his back pocket. He has 6,000 electrons in his back pocket. I'm still after him, though. And I'm still going to hire my wife as the agent who's going to take your electrons. So because you're going to lose electrons, what happens to you?
I get oxidized.
You're getting oxidized. My wife was the agent who caused you to get oxidized. So we call her the oxidizing agent. But she actually gained those electrons. And so it seems weird, but the oxidizing agent, the agent that causes oxidation, actually gets reduced. So it seems backwards, but the oxidizing agent gets reduced, the reducing agent gets oxidized. It's so kind of funky on the nomenclature, but that's why they name it the way they do. Another name for oxidizing agent is oxidant. Another name for reducing agent is reductant. So let's look at this for a minute. Common questions is you'll get a reaction. It may or may not be balanced. Like here, this one's not balanced. But they may say, who gets oxidized? Well, okay, we can answer that. So who's getting oxidized here? I. Because here, iodine is going from -1 to 0. His oxidation state is going up. He lost an electron. Okay. Who's getting reduced then? So what was manganese's oxidation state to start? +7, and he ends up as, that's all +2 is him. Okay, and so we can see that he's getting reduced. He gains 5 electrons to get there. Now here's the deal. When they ask for the species that gets oxidized or reduced, it's always a reactant, never the products. It's always the reactants that get oxidized or get reduced. If they ask for who's the reducing agent or the oxidizing agent, same thing. It's always reactants, never products. Now here's the last part of this. So if I ask for who gets oxidized, you could state this 2 ways. You could say I is the element that gets oxidized, or you could specifically say the exact chemical species is actually I-. Either one of those is an acceptable answer. If I ask you for who gets reduced, you have 2 options. You can say that Mn, manganese, is the element that is getting oxidized. He's a particular element. Or you could say what chemical species he actually exists as, which is MnO4-. So you could say manganese is the element, specifically the element, or it's really the entire reactant molecule, or ion in this case, is permanganate ion. And either one of those is correct. Now here's the deal. The moment, though, we start talking about the reducing agent, again also called reductant, or the oxidizing agent. Now, the only acceptable answer is the exact chemical species. And so in this case, the reducing agent got what? Oxidized. And so in this case, though, the exact chemical species is not just I, it's I minus would be the correct answer. The iodide ion is the reducing agent. Who's the oxidizing agent? The entire chemical species is MnO4 minus. So if you're talking about the agent, you got to get specific of the exact chemical species as it exists on the reactant side.